where L is equal to lambda over 2 or lambda is equal to 2L. Example 1. A pipe closed at one end is 1 meter long. The air in the pipe is set into vibration and the fundamental note is produced. If the velocity of sound is 340 meters per second, calculate the frequency of the note. Figure 3.9. L is equal to 1 over 4 lambda, which is equal to lambda over 4. Therefore, lambda is equal to 4L. V is equal to F lambda. Making F the subject of the formula, you have F equals to V over lambda, which is equals to V over 4F. If you substitute lambda, which is equals to 4L, then substituting the values, we have 340 all over 4 times 1, which gives us 85 hertz. Example 2. In a resonance tube experiment, figure 3.10, the frequency of the tuning fork 750 hertz and the resonating length of the air column is 0.3 meters as shown. Calculate the velocity of the wave. Solution. At second resonance, L1 is equal to 3 over 4 lambda, but resonating length of air column L1 is equal to 0.3 meters. 0.3 is equal to 3 over 4 lambda. Lambda is equal to 0 over 3 times 4 all over 3, which is equal to 0.4 meters. From V equals to F lambda, substituting the values, we have V equals to 750 times 0.4, which is equal to 300 meters per second. Example 3. Calculate the length of the air column in a tube closed at one end required to produce a note whose fundamental frequency is 350 Hz. The speed of sound in air is 330 meters per second, neglecting the air coordination. Okay. Solution. Fundamental frequency FO for a closed tube is given by FO equals to V over lambda, which is equals to V over 4 lambda, where L is equals to lambda over 4 or lambda is equals to 4L. Using V equals to F lambda, therefore V is equals to F lambda. V equals to FO 4L. Making L the subject of the formula, we have L equals to V over 4L. Substituting the values, we have is equals to 330 all over 4 times 350, which will give us 0.24 cm. Example 4. In a sound wave in air, the adjacent refraction and compression are separated a distance of 17 cm. If the velocity of the sound wave is 340 meters per second, determine the frequency. Solution. Velocity of sound wave V is equal to 340 meters per second. Wavelength of sound wave equals to 17 cm, which is equal to 0.17 meters. Frequency of sound wave F is unknown. From V equals to F lambda, therefore, substituting the values, we have V 340 is equal to F, which is unknown, times 0.17 for the lambda. Making frequency F the subject of the formula, we have F equals to 340 over 0.17, which gives us 2000 Hz. Example 5. In a resonance tube experiment, the effective length of the air column for the first resonance is 20 cm when set into vibration by a tuning fork of frequency 480 Hz. Neglecting the air effect, calculate the velocity of sound in air. Solution. At the first resonance inside the tube with one end open is given by L is equal to lambda over 4. Therefore, lambda is equal to 4L. V is equal to F lambda, which is equal to 4LF. Therefore, V is equal to 4 times 0.2 times 4H, which will give us 384 meters per second. Example 6. An organ pipe closed at one end is 80 cm long. Determine the frequency of the fundamental note, assuming that the speed of sound in air is 340 meters per second. Solution. The fundamental frequency FO for a closed pipe is given by FO equals to V over lambda, which is equal to V over 4L. L is equal to 80 cm, which is equal to 0.8 meters, and V is equal to 340 meters per second. Therefore, FO is equal to 340 over 4 times 0.8, which will give us 106 Hz. Example 7. Two tuning fork of frequency 256 Hz and 260 Hz are sound close to each other. What is the frequency of the beat produced? Solution. The frequency of the beat produced is obtained by finding the difference between the two nearly equal frequencies. Therefore, the frequency of the beat produced is equal to 260 minus 256, which will give us 4 Hz. Example 8. Calculate the frequency of the first overtone of a closed pipe of length 20.0 if the end correlation is 0.7 cm and the velocity of sound is 340 meters per second. Solution. Wavelength is equal to 4 in brackets L plus C, which is equal to 4 in bracket 20 plus 0.7, which will give us 82.8 cm. Fundamental frequency FO is equal to V over lambda, which is equal to 340 all over 828 times 10 raised to the power minus 2. First overtone is equal to 3FO, which is equal to 3 times 340 all over 82.8 times 10 raised to the power minus 1, which will give us 1232 Hz. Application of sound wave. Dependencies on frequency, on length, mass and force or tension. Laws of vibration or a fixed range. Frequency of fundamental of a stretched string is given by F equals to 1 over 2L square root of T, that is period capital T over M mass. Writing F for FO, it thus follows that 1. Frequency F is inversely proportional to length L. F is inversely proportional to 1 over T for a given tension T and string M constant. 2. Frequency F is proportional to the square root of the tension F is proportional to square root of T for a given length L and string. 3. Frequency F is inversely proportional to the square root of masses per unit length. F is proportional to 1 over square root of M for a given length L and tension capital T. Example 1. A sonometer wire of length 100 cm under tension 10 Newton has a frequency of 250 Hz. Keeping length of wire constant, the tension is adjusted to produce a new frequency of 350 Hz. What is the new tension? Solution. Suppose T is the required new tension. Since F is proportional to square root of T, therefore